All right, let's get into it. Today we're going to peel back the curtain on the hidden science that makes some products just feel so right. You know, why they look amazing and seem like they're built to last forever.
Think about it. When you pick up your phone, or a really nice kitchen knife, or even a precision-made car part, have you ever just held it and thought, wow, what gives this that satisfying premium feel? It's that unmistakable sense of quality, right? That smoothness, that perfect weight.
Well, here's the secret. It's not just about using expensive metals. The real magic is happening on a microscopic level. And this is where we get into the cool stuff, advanced surface engineering. It's a whole field dedicated to turning ordinary materials into something extraordinary.
So, what's the big problem that surface engineering is trying to solve? Well, it all comes down to a fundamental challenge, this dual mission that every product designer has to tackle, the constant battle between how something looks and how it works.
It's a real balancing act, you know? On one hand, you've got aesthetics. You want that amazing look, that premium finish. But on the other hand, you need function. It has to resist wear and tear, it can't rust, and it's got to be durable. The genius of surface engineering is that it lets you nail both at the same time.
So how in the world do engineers actually pull this off? Well, they've got this incredible toolkit of high-tech processes. Let's dive into a couple of the most important ones.
Okay, first up is something called plasma electrolytic oxidation, or PEO for short. Now just imagine this. You take a lightweight metal, like aluminum, and you use a high-voltage electrical bath to literally grow a super hard ceramic-like shield right out of the metal itself. It's not just a coating sitting on top, it becomes an integrated part of the surface.
And the results? They're pretty awesome. You get surfaces that are incredibly hard and resistant to wear. It works perfectly on light metals like aluminum and magnesium. And the best part is that engineers can fine-tune the whole process to get the exact look and protection they're going for.
Now what if you need to get even more precise? Well, that's when you bring in the lasers. This is called laser surface texturing, or LST, and it's basically like microsculpting with pure light. You're using these incredibly precise lasers to carve microscopic patterns onto a surface, which fundamentally changes how it looks, feels, and even how it behaves.
So what can these tiny patterns do? A whole lot, actually. These microgrooves can make a surface way more resistant to corrosion, they can give coatings something better to grab onto, and of course, they can be used to create some absolutely stunning visual effects and finishes.
You know, to really appreciate how cool these new methods are, it helps to see them next to the older techniques. Take high-velocity oxygen fuel spraying, HVOF. It's a modern way to apply these super tough coatings. Now compare that to old-school hard chrome plating. The difference is night and day. HVOF gives you this uniform, super hard surface, while chrome plating is notorious for cracking and has some serious environmental issues.
And here's the kicker. The data shows that these advanced HVOF coatings can provide a 5-fold increase in corrosion resistance compared to hard chrome. I mean, 5 times. That's not just a small bump, that is a massive leap forward in performance and how long a product is going to last.
Okay, so creating these amazing surfaces is one thing, but how do scientists actually prove that they work as advertised? That's where a whole suite of really rigorous testing comes into play. Let's look at a classic one, the wear test. The idea behind it is actually pretty simple. You take your coated sample, you press a standardized little pin or ball against it with a very specific amount of force, and then you just slide or rotate it for a while. Afterwards, you can measure exactly how much wear and friction occurred. This gives you cold, hard data on just how tough that surface really is. But that's just one piece of the puzzle. The full testing arsenal is seriously impressive. Scientists use massive scanning electron microscopes to literally see the surface structure. They run electrochemical tests to check for corrosion resistance. They even use these salt spray chambers to simulate years of harsh weather in just a few days. It's an incredibly thorough process. So all of this incredible science is leading somewhere really, really exciting. Let's take a look at where surface engineering is headed, because this is where things start to get smart.
The big idea here is that surfaces won't just be passive layers of protection anymore. No, the next generation of surfaces will be active, intelligent, and in a lot of ways, totally self-sufficient.
A perfect example of this is something called super hydrophobic coatings. These are surfaces that are engineered at the nanoscale to repel water like you've never seen before. Water doesn't just beat up on them, it forms these almost perfect little spheres that literally roll right off and they take dirt and grime with them. We're talking about self-cleaning and even anti-icing surfaces here.
And here's the number that proves it. On a normal surface, a water droplet might sit at a 90-degree angle, but on these super hydrophobic surfaces, that angle is greater than 150 degrees. That shows you just how extreme the water repellency is. It's incredible.
So how are we going to design all these crazy new surfaces? With something called digital twins. It's exactly what it sounds like, a perfect virtual copy of a product surface that lives inside a computer. Engineers can simulate everything, the heat from a laser, the flow of particles, all the resulting stress, and perfect the entire process in the virtual world before they ever make a single physical part. It's totally revolutionizing how quickly we can innovate.
So, the big takeaway here is this. We're stepping into an era where a product surface isn't a limitation anymore. It's a canvas for innovation. And that leaves us with a really fascinating question to think about. If we can engineer any look, any feel, and any function directly into a material, what will the products of tomorrow really be capable of?